Thank you for the invitation and the introduction. All right, so I want to talk about the low canonical threshold on Fano varieties. So let me just define what low canonical threshold is. And first, so like here, variety always assumed to be smooth and defined over complex numbers, unless otherwise mentioned. Okay. So suppose we have a variety x, and suppose you have the effective integral divisor on x, then we can define the low canonical threshold by this number. So you take some numbers, I mean positive numbers, and you consider this pair, and then so like such that this pair is the canonical, low canonical, and then we take the Springer. Right? Then this number is called the low canonical threshold. Right? Right, this is pretty much a standard notion in variational geometry. And next, I'll introduce a little bit new notion about defined by the low canonical threshold. So suppose you have a smooth Fano variety, and then you took some natural number m, then we define the mth global low canonical threshold of x by this number. So you take all like purely anticanonical divisor, which lives in the minus nkx, and then you take you divide this divisor by m, and then you calculate the low canonical threshold of this pair, and then you take the minimum, I mean the infimum. So this is called the mth global low canonical threshold. Okay. And then we define the global low canonical threshold of x. So you collect all the mth global low canonical threshold. This is supposed to be m. Okay. So and then you take the infimum among them. So that means that if lambda is at most the global low canonical threshold, then you choose the arbitrary q divisor, which is numerically equivalent to the anticanonical divisor, then this pair is always low canonical. So that number measures the singularity, I mean the worst singularity of the q, effectively q divisor, which is numerically equivalent to minus kx. Right? That's the notion. So you might be wondering why we define this number. So there's a nice application. I mean there are several applications, but I think this is the more or less famous. So there is some application to Kerr-Einstein metric on the Fano varieties. So first of all, like let me define what Kerr-Einstein method is. So the Kerr-Einstein method is defined in the following way. So a compact complex manifold is said to be Kerr-Einstein if it has the Kerr-Einstein metric. So Kerr-Einstein metric is the Kerr form. So in this way, and then that satisfies the Einstein condition, which means this Ricci curvature is the constant multiple of this Kerr form. If this Einstein condition is satisfied, then we said this manifold is the Kerr-Einstein manifold. Okay? So this is a rather famous definition for the. So in particular, this Kerr-Einstein metric, existence of Kerr-Einstein metric related to some partial differential equation, which is called the Monge-Ampere equation. So if it has the Kerr form, which satisfies the Monge-Ampere equation, then that is the Kerr-Einstein metric. Okay. So related to the global low canonical threshold, the Demai, Kolar, and Nettle, and Tian Yao proved the following statement. Actually, it started from the Nettle in 1990, I guess 1992, and then Tian Yao and the Demai, Kolar developed this theory. So the theorem says if X is the n-dimensional Fano variety, then if this global low canonical threshold is strictly bigger than dimension over dimension plus 1, then it has a canonical metric. So this, this theorem, like, is bridge between this global low canonical threshold and this Kähler geometry. Okay. All right. So let me show you the easiest case. So, like, I think it's year 2006 or 7. So Charles proved this. He computed all the global low canonical threshold for the smooth Delphi surface. So, for example, like easy case is this. So, like you have, suppose you have the smooth Delphi surface, degree 9, then you can easily compute that global low canonical threshold is 1 over 3 always. And for example, like degree 8, or for example, like a P1 plus P1, you can easily calculate the 1 over 2, and then so on. So if degree increased, then this global low canonical threshold is increased. So for example, like here and here, here and here, up to here. So if degree is smaller than S, the computation is not simple. You have to do something like you have to work hard to get these numbers. But somehow we can, the Charles computed the older numbers. So like if you see this number, the dimension is 2, so like to guarantee the existence of Kähler metric, you have to have the greater than, the global low canonical threshold greater than the 2 over 3, right? So here, from this, so you can see cubic surface without Eckart point, and the differential surface of degree 2 and degree 1 always have the Kähler metric. Here, you can see from here. So
is it sharp?
What do you mean?
Case.
Which case?
The cubic with the Eckart point, for example.
Yeah, this is Eckart point. With the Eckart point, this is sharp. Eckart point means that you have.
In that case, it doesn't have a Kähler metric.
I will explain later. All right. So this, this is just a sufficient condition, not the necessary condition. So you can say more. So like from the theorem, so you can say the smooth surface, differential surface of degree like M-2 always admits the Kähler metric, and the general smooth cubic surface admits the Kähler metric. So that's immediate. But for example, here you can say actually the Tian proved the existence of the Kähler metric smooth temperature surface. He completely classified which temperature surface has the Kähler, which one does not have the Kähler metric. So for example, like here, I said like 2 cases. Except these 2 cases, except these 2 cases, every temperature surface has the Kähler metric, which was proven by the Tian, like 20 years ago. So, like for example, like these 2 temperatures, these 2 types of the temperature surface, there is just some obstruction to have the Kähler metric, which is the stability slopes. Actually, the K stability, but you can easily, one can easily show that this the 1-point blow up of the P2 is not stable. Slope stable with respect to the anticanonical divisor. So which means it does not have the metric which has the constant scalar curvature. So that means it does not have the Kähler metric. And the aperture surface, I mean smooth aperture surface of degree 7 case also, actually this guy is the slope unstable, I mean slope stable, but it's not case stable. So that means, I mean, if the surface, I mean the manifold has the constant scalar curvature metric, then it must be the case stable. So that means this guy is not, I mean, it's not Kerr-Einstein. Okay. So except these two aperture surface, every aperture surface, smooth aperture surface, contains, I mean, the admits the Kerr-Einstein metric. Okay. All right. Okay. All right, and now we consider the aperture surface with the Duval singularities, and we want to calculate the global local threshold of them. So, like my students, Won and we proved if, I mean, suppose S is the aperture surface only with the Duval singularities, and suppose the degree is n is 3, then the first, I mean, global local threshold is always equal to the first global local threshold. So in this case, you can easily compute these numbers. Actually, I can list these all numbers, depends on the singularities, but it requires a lot of spaces, so I omit the table. But if degree is n is 3, then the first global local threshold is the same as the global local threshold. You just consider the hyperplane section, I mean the anticanonical divisor, and then you look at how they look like. Then you can easily compute. Okay. And the degree 2 case, I mean the aperture surface with the Duval singularity of degree 2. All right, then depends on the singularity types. You can compute the global local threshold. So in this way, I listed the global local threshold, and you can see if, I mean, you can easily check if the singularity type of this temperature surface is neither A7 nor A6, and you can check the first local threshold is always same as the global local threshold. But degree 7 case, I mean the A7 case, A6 case, so you can see this global local threshold is coincide with the second global local threshold, not the first global local threshold. All right, and not this one. And for the degree 1 case, the Dimitrov Costa has completely computed the global local thresholds. So in this case, I mean, and you see the degree 1 case, it has a lot of singularity types. I mean, only for the Duval singularities. So it takes, I mean, if I list the older case, then it takes several pages. But I just listed the several cases which only has the secret types. So here in this case, I mean, if S is the aperture surface with the Duval singularity of degree 1, and if the singularity types are the following, then we can check the global local threshold always strictly bigger than the 2/3. So Kerr-Einstein metric means that you have the obifold Kerr-Einstein metric. So you consider the obifold neighborhood, and you go upstairs, and then on the upstairs you have the Kerr-Einstein metric, which is invariant on the group action. Okay? So in this case, so S has the Kerr-Einstein metric. All right, And before I go further, so let me explain the other application. So you can also like compute the global mechanical threshold of the differential surface with the only with the cyclic quotient singularities. So and then you can use the same criterion for the Cayley-Einstein metric. All right. So if global mechanical threshold is strictly bigger than 2/3, then it has the orbifold Cayley-Einstein metric, right? All right, and then you consider some like S1 bundle over the differential surface, I mean circle bundle. Then that gives us real 5 manifold. And then if this differential surface admits the Cayley-Einstein metric, then that implies there is, I mean, this circle bundle admits the Sasaki-Einstein metric. So, like, and this is the one of the mainstream, I mean, for the 5 manifold classification. I mean, there is some guys who is working on the like Sasakian like geometry on 5 manifold, and they want to find the like Sasaki-Einstein metric. So what they use is they study the like, for example, like the differential surface the differential hypersurface in the weighted projective space, and then which has the cyclic quotient singularities, and then they like study whether this guy has the Cayley-Einstein or not. And then if they have Cayley-Einstein metric, then they construct the circle bundle over that differential surface. And then they study the topological type of the circle bundle. There is some like algorithm to find the topological type of this real 5 manifold. And then because of the Cayley-Einstein metric on the bottom, this circle bundle admits the Sasaki-Einstein metric. So that's the way to finding a Sasaki-Einstein metric on the 5 manifold. That's what they do. So like if you study the global mechanical thresholds of the differential surface with the cyclic quotient singularity, you can get some like a result of the Sasaki-Einstein metric on the 5 manifold. So that's the another application related to Cayley-Einstein metric on the differential surface. Okay. All right. And let's go up. So now we consider like a higher dimensional variety. So first of all, we consider like a smooth hypersurface of degree m+1 in Pm+1, right? Which is Fano, primitive Fano. Right? In this case, we can prove. So Chertsov and I proved like a long time ago, we proved the global global mechanical threshold always at least n over m+1. And this inequality, this equality holds if and only if X contains the cone over dimension n-1. Okay. So this inequality shows the global mechanical threshold is at least n over n+1. Right? And if the hypersurface X contains the cone over dimension n-1, then you can say, like, the global mechanical threshold is exactly n over n+1. Right? But if X does not have the cone over dimension n-1, then what you can say is just like the global mechanical threshold is n is n over n+1. It doesn't improve because the global mechanical threshold is defined by infimum, right? You may have the sequence to the n over n+1, right? So this bound is not enough for the existence of the Caron-Stein metric on the hypersurface. That's the problem, right? All right, but I think that this is in year 2002, Puklikov proved if X is a general hypersurface of degree n plus 1, and this is n is 6 in Pn plus 1, then the global low chemical threshold is 1. So that means that means if in this case you can say general hypersurface has admits the Caron-Stein metric, right? And this because 1 is definitely bigger than n over n plus 1.
In the previous theorem, you mean a cone of the same degree of dimension.
Yeah, that's true.
Same
Yeah,
degree.
yeah. Right. Okay. But somehow he couldn't prove the low dimensional case. So, for example, so that he conjectured a global low chemical threshold of general quartic 3/4 and general quintic 4/4 are 1. But this conjecture is still open. But actually, the Puklikov was working on the bidirectional rigidity problem. So his question is like this, like, quartic 3/4 is the non-rational, known to be non-rational. So he wants to take the product of two quartics, quartic 3/4. And then he asked the same question, whether this guy is the rational or not. So what he did, to say, in this case, if you take the general hypersurface of degree n plus 1 and it's the 6, you take suppose you take the product of these two general hypersurface. This guy is not, this x is not rational, but cannot, it's not a simple question. If you take the product of these two types of the general hypersurface, then you ask whether this guy is the rational or not. But the simple guess is the non-rational, right? Everybody expects it should be non-rational, but it's hard to answer. But to prove that, he needs this condition. So that's another application for the global low chemical threshold. For the rationality problem, we need the global low chemical threshold is 1. But for the Caron-Stein problem, so you need the dimension over dimension plus 1, right? So 1 or 2 years ago, when Chersov and my student Wang and I, we proved the general quartic, hypersurface X has the global low chemical threshold and is 16 over 21, which is bigger than 304, right? This is 304, definitely. So, which means then general quartic hypersurface always admits the Caron-Stein metric, right? Confusion. All right, and also we proved the general quintic hypersurface X in P5, the global low chemical threshold is at least 22 over 25, which is bigger than 4 over 5, right? So that means general quintic hypersurface admits the Caron-Stein metric always. Right? So, but the conjecture, this conjecture is still open. We need the 1 for the rationality problem. Right? But somehow we cannot handle, we need more somehow new general conditions, but we couldn't find it yet. So like here, a general hypersurface of degree n plus 1, and it's the 2 in the Pn plus 1 has always the Caroline-Stein metric, right? For the if n plus 1 is 2, I mean the n is 1, then it's just a smooth conic, right? Smooth conic is the isomorphic to P1, and it has the Pugliese-Studi metric, which is Caroline-Stein, so always. And if n is 2, then it's the cubic surface. And in this case, always, I mean, since cubic surface always have the Caroline-Stein metric due to the Tian's proof. All right. And next Fano variety is the double curve of Pn ramified the hypersurface of degree 2n, right, which is Fano also. Okay. So in this case, we also prove the global local threshold of this guy is at least 1 minus 1 over 2n, which is bigger than the n over n plus 1. Right? So this guy has the Caroline-Stein metric also. Right? So the proof is like the global local threshold is given by the actually the hypersurface of S. I mean this ramification divisor, like this hypersurface S of degree 2n in Pn. You calculate the sort of like global local threshold, sort of. I mean given by the hyperplane section. I mean you consider like every effective divisor here, which is numerically equivalent to the hyperplane section. And then you take the same procedure, and then you take the supremum number, which makes that divisor. I mean, that type of the divisor is the low canonical, right? And then you take the 1/2 for the summation. That's the global low canonical threshold of this guy, because this is the double cover. So you always have if you write down this variety, I mean the equation of this double cover in the weighted projective space, then you always have like a W squared equation, right? So for that reason, you always have the 1/2 plus, and this the global low canonical threshold for the S. So that's why you have this number. Okay. So, like as I said, a smooth double curve Pn ramified along hypersurface of degree 2n, and is therefore there is always the Caroline-Stein metric. Actually, there is the analytical proof by these three guys. So they use the analytical method, and they obtain the more general result, which covers this case. Okay? So, which means so you may consider like a double curve ramified hypersurface degree like at most 2n. In that case, also the Fano, right? In that case, I mean, with some restriction on this degree, and they can prove that type of the Fano variety against the Caroline-Stein metric. So that's another story. But Puklikov actually I mean here what he proved is this guy, I mean this is for the every smooth double curve. Okay? But Puklikov proved the general case. I mean if V is the general double space, and if n is n is 3, then the global low canonical threshold in this case is always 1. So you can apply this global low canonical threshold to the rationality problem of the product of Fanos. Okay. All right. And then here, from now on, I want to compute the global low canonical threshold, the complete intersection of the quadric and the cubic in P5. Right? So suppose you have the general complete intersection of the quadric and cubic in P5, which is Fano also. Fano of degree 6. And the question is, what is the global low canonical threshold in this guy? So the statement is, this number is at least 3 or 4. Okay? So proof is like this. So, all right. So here, all right. So first of all, like you consider the tangent space. You choose the one point, and then you consider like a tangent space. This is the this is the three-dimensional like linear subspace in P5, right? And then you take the intersection with the W, then you get the one cycle, right? Then this cycle ZP is one of the following always. So ZP is a irreducible rational sexy curve with the quartic point at P, or like some of the rational quintic curve with a triple point at P and their line, which passing through the point P, or like a irreducible rational quartic with a double point at P and two lines passing through the P, or smooth cubic curve and the three lines passing through the point P. And the ZP also, moreover, ZP has the ordinary singular point at the point P. Because our W is the general. You see, because this is the why you have this 4 types of the one cycle. See here. All right, so suppose your complete intersection given by the quadric hypersurface W2 and cubic hypersurface W3, and you fix the one point, and then you fix the system of affine coordinate Z1 up to Z5 with the origin at P. Then you get for W2, you can write the equation like this. For the W3, you can write the equation like this, right? Okay, and then you put the 0 for the Z4 and Z5. Then you get these equations from this, right? Then that condition, this condition means and this, right? F2 is non-zero and irreducible, and F2 and Z2 defines 4 distinct points in P2, and this Z3 cannot pass through more than 3 points of this 4 points at every point. So by dimension counting, you can prove this is the general condition. If the complete intersection is the general, then this ZP must be one of these 4 types. Okay. And then you consider D is the effective Q divisor, which is numerically equivalent to anticanonical divisor. And then you put some number, lambda, and then you suppose this guy is not low canonical at a point P. This V is supposed to be W. Okay. So in the complete intersection. Right. Then, because this guy is not low canonical, the general theory tells us the multiplicity of the D at the point P is strictly bigger than 1 over lambda. Okay, and then you take the blow-up at the point P with the exceptional divisor E, then inversion of a junction tells us that there is a line L in this the exceptional divisor such that the multiplicity of D at the point P plus multiplicity of D bar, which is the strict transform of D by pi, along the L is strictly bigger than 2 over lambda. Moreover, if you take the here S is the general hyperplane section, which is tangent to the W, I mean V here at the point P. If you take the intersection with this guy, the multiplicity of this guy is always 3 over lambda. You can show that. All right, and then we analyze every 4 cases. So suppose like the one cycle is irreducible, right? Then that is just the static curve in P3. All right, then you take the general member here. I mean, this is the set of a hyperplane section which tangent to the W at the point P. And then you write it in this way: M times C6. Actually, the C6 is the ZP here, and some like a residual part here, which does not contain the C6, like this. Right? You see, and then you take the general hyperplane section M, and then you take the intersection, then you get 6 because our Fano has the degree 6, right? And then you see this guy is a degree 6, so you get 6 times M plus and this number, right? And this is this is a big, I mean N is the 6 times M because this number is the positive, right? That means M is less than 1. I mean less than or equal to 1. Right? All right, and then you take the general member here. This means the hyperplane section tangent to the point P, right? So here you have 6 here, and this D times S, and this times H, right? So this is the 6M plus delta times H, right? Right, and then this is 6M, and this number is bigger than what? So this is this 2 comes from the multiplicity of this guy at the point P, and the multiplicity of this is what? DS, D times S has the multiplicity, they are strictly bigger than 3 over lambda at the point P, right? So this guy has the multiplicity 4 at the point P, so this is the multiplicity, I mean the bound for the multiplicity of the delta. So you get the others. Then this is the 6 over lambda minus 2m, and the m is at most 1. So you get the lambda over, 6 over lambda minus 2. So that means 8 as n is the 6 over lambda. So you get this number. Right? All right? Let me go further. Now, suppose you have the ZP is the sum of the irreducible pointing with the triple point at the point P, and suppose that your line L1 passing through the point P. Right? Then D times S, you can write the D times S in this way. Okay? Right? And then what you're going to do is this. We need this bond. To get this bond, all right, S is the K3 surface. Only with the ordinary double points at the point P. Right? Because S comes from the tangent hyperplane section. Right? Right. Then you blow up. This guy C5 is the rational curve because it has the singularity. The multiplicity 3 points, right? and L1 is the rational, and it passed through the A1 point, right? And then you blow up, and then you analyze the intersection numbers, right? So every information is given for this intersection numbers. So you can easily calculate this number, 502 and the 502, and for this line, the self-intersection number is the -3/2, right? And then you take the intersection, C5 with the ds, then you get C. This is a 5 because this guy is the degree 5, right? And then you have this expression. And this number is at least 5/2m plus 5/2m1, right? Then you get this inequality. Right, and then again we take the intersection with the general member here, so you get 6, right? You have this number, right? Then this is the hyperplane, so you get the degree 5 curve, so you have 5m line with the hyperplane, you have the m1, and the residual part here. Again, the multiplicity of the delta at the point P is at least 3/lambda minus 3 minus m, the minus 3m minus m1, right? And then you get the 6/lambda minus m minus m1, which is by our bound here. This number is the m was 2, so you get the 6/lambda minus 2. Again, you have the 3/4, right? And other cases are the same. So you write down in this way, and then you calculate the intersection numbers, and then you got the reasonable bound for this, and then you take the intersection with the general member, and you always end up with the 6/lambda minus 2, right? And then you always get the 3/4 here. And for this case also, right, you have the intersection numbers here, and you get this bound, right? Then you calculate this number. Again, you end up with the 6/lambda minus 2. So you can see this lambda must be bigger than 3/4, right? Which means the global Lopez threshold of our general complete intersection of the quadric and cubic is at least 3/4. But unfortunately, this bound is not enough for the Lagrange dimension. And I don't know yet whether this bound is sharp or not. I need more study for this. Right? Right, thank you.
Any question?